Namaste, my friend, and welcome back to JEE Chemistry with Typical Monk. This is class 2, and today we go where no eye can follow, inside the atom itself. Sit with this for a moment. Nobody has ever seen an atom. It is far too small for any microscope. Yet we can tell you exactly where its center sits, and we can read the colors of light it gives off like a fingerprint. When Sarah first heard this, she asked the honest question, if we cannot see it, how do we know any of it? That is the whole adventure of today. We learn the inside of the atom entirely from the outside, by bouncing particles off it, by reading the light it glows with, and in G, by turning that light into a full numerical E. So take a slow breath. Let us step inside, one idea at a time. So what will you carry home from today's class? First, the discovery of the electron, the proton, and the neutron, the three particles every atom is built from. Second, three models of the atom, Thomson, then Rutherford, then Bohr, and just as important, why each one had to be replaced by the next. Third, Bohr's energy levels, the hydrogen spectrum with its Lyman, Palmer, and Paschen series, and the Rydberg formula that ties them together. Fourth, the modern picture, the photoelectric effect, the dual nature of light and matter, the Broglie's waves, and Heisenberg's uncertainty. And fifth, the G drills, assertion and reason, match the column, and the numericals. So everything you learn today, you can also score with. Ready? One idea at a time. Let us walk through the atom story, piece by piece. First, the electron. Thomson passed a beam through a cathode ray tube and found a tiny negative particle hiding inside every atom. He pictured the atom as a soft sphere of positive charge with electrons dotted through it, like raisins in a pudding, the plum pudding model. Second, the building blocks of the nucleus. Goldstein sent a beam of positive rays the other way and found the proton. Years later, Chadwick found a third particle carrying no charge at all, the neutron. Three particles, one atom. Third, Rutherford fired alpha particles at a thin sheet of gold foil. Most sailed straight through, but a few bounced sharply back, as if they had struck something tiny and hard. David said it felt like firing bullets at tissue paper, and having one come back at you. Rutherford concluded the atom has a tiny, dense, positive nucleus at its center, with the electrons far outside. The pudding was gone. And fourth, Bohr fixed the one problem Rutherford could not solve. A moving electron should spiral into the nucleus and collapse. Bohr said electrons move only in certain fixed orbits, each with a definite energy, and while an electron stays in its orbit, it does not radiate at all. Every model was a repair of the last. Look at this ladder carefully, because it is the map for every spectrum numerical in this chapter. Each rung is an allowed orbit, and the higher the rung, the higher the energy. First, each orbit has one fixed energy. For hydrogen, the energy of level n is minus 13.6 over n squared in electron volts. Second, here is where light comes from. When an electron falls from a higher rung to a lower one, it gives out a photon, a packet of light whose energy is exactly the gap between the two rungs. Third, the landing rung decides the family of light. Land on the first level and you get the Lyman series, in the ultraviolet. Land on the second, the Balmer series, invisible light. Land on the third, the Paschen series, in the infrared. And fourth, notice every energy carries a minus sign. That minus is not a mistake, it means the electron is bound, trapped by the nucleus. Zero energy is the top of the ladder, where the electron finally breaks free. Lisa remembers it this way. The deeper the well, the more negative, and the harder to escape. Now, let us turn those energy gaps into the exact colors we see. First, the two directions. When an electron drops to a lower level, the atom gives out light. That is emission. When it climbs to a higher level, it takes light in. That is absorption. Same ladder, opposite direction. Second, the Rydberg formula ties it all together. 1 over the wavelength equals the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. Here, n1 is the lower level and n2 is the higher one. Third, and this is the trick that saves you every time, the lower level, n1, names the series. Land on level 1, it is Lyman. On level 2, Balmer. On level 3, Passion. And fourth, of all these families, only the Balmer series falls in the visible range, the light your eye can actually see. That is exactly why it is JEE's most examined series, and the one we solve fully next. Time to solve a full JEE numerical together, slowly, the monk's way. A hydrogen electron falls from the third level to the second level. The very first line of the Balmer series, called H-alpha. JEE will ask for both its wavelength and its energy. Step 1. Write down what is given. The electron falls from n equals 3 to n equals 2, and the Rydberg constant is 1.097 into 10 to the power 7 per meter. Never skip writing the given. Step 2. The formula. 1 over lambda equals the Rydberg constant times 1 over n1 squared minus 1 over n2 squared, where the lower level n1 is 2 and the upper level n2 is 3. Step 3. Compute the bracket. 1 over 4 minus 1 over 9 is 5 over 36. So 1 over lambda equals 1.097 into 10 to the power 7 times 5 over 36, which comes to 1.524 into 10 to the power 6 per meter. Step 4. Solve for lambda. Flip that number over and lambda comes to about 656 nanometers. Visible red light, exactly the Balmer H-alpha line. Step 5. The energy. Energy equals hc over lambda, and working that through gives about 1.89 electron volts. The very same number you would get by simply subtracting the third and second Bohr levels. 2 methods, 1 answer. That is how JEE checks that you truly understand the ladder. Now the ideas that broke classical physics wide open. First, light does not arrive as a smooth stream. It arrives in packets called photons, and each photon carries an energy equal to Planck's constant times its frequency. Second, shine light on a metal, and above a certain threshold frequency, a photon can knock an electron clean out of the surface. Here is the surprise that trapped everyone. Making the light brighter ejects more electrons, but never faster ones. Speed comes from frequency, never from brightness. John found that backwards at first, and so does most of the country in the exam. Third, so light behaves as both a wave and a particle at once. Its dual nature. And fourth, de Broglie made the Bohr leap. If light can be a particle, matter can be a wave, with a wavelength equal to Planck's constant divided by mass times velocity. And Heisenberg went further still. Position and momentum of a tiny particle like an electron can never both be known exactly at the very same instant. Together, these two ideas are exactly why Bohr's neat fixed orbits could not be the final picture. Now sit up straight. These 5 lines are what JEE actually asks, year after year. 1. The energy of a hydrogen level is minus 13.6 over n squared in electron volts. Memorize the first 3 values called minus 13.6, minus 3.4, minus 1.5. 2. A spectral series is named by the level the electron lands on, Lemon on 1, Balmer on 2, Passion on 3, and Balmer is the visible, most tested line. 3. In the photoelectric effect, kinetic energy equals h nu minus the work function phi. Frequency decides whether electrons come out and how fast. Intensity decides only how many. 4. De Broglie's wavelength is Planck's constant divided by mass times velocity. Heisenberg's uncertainty says the product of the uncertainty in position and the uncertainty in momentum can never fall below h over 4 pi. 5. The Bohr model fails for multi-electron atoms, and it quietly violates Heisenberg's uncertainty by pretending both position and speed of the electron are known at once. Know its limits, not just its wins. Let us drill the JEE way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion, the Balmer series lies in the visible region. Reason, Balmer lines are the ones that end on the level n equals 2. Think like Sarah, check each statement alone, then check the link. Is the assertion true? Yes. Is the reason true? Yes. And does it explain? It does, because landing on the second level gives just the right energy gap to land in visible light. Both true. Reason explains. Option A. Second one. Assertion. Increasing the intensity of light increases the kinetic energy of the photoelectrons. Reason. The kinetic energy of photoelectrons depends only on the frequency of light, not its intensity. Check the reason first. True. Exactly the lesson of today's class. Now the assertion. False, because brightness only changes how many electrons come out, never their speed. Assertion false, reason true, option D. Third one. Assertion, the Balmer alpha line has a wavelength of about 656 nanometers. Reason, Heisenberg's uncertainty principle allows the position and momentum of an electron to be measured simultaneously with complete accuracy. Check the assertion first. True, exactly the number from our worked example. Now the reason. False, because uncertainty says the very opposite. Position and momentum can never both be pinned down at once. Assertion true, reason false, option C. This is the trap that catches John every time. A true first line, and the reason that quietly reverses the actual rule. A quick match now. Say each answer aloud before I reveal it. The Lyman series. It ends on the first level, and its light is ultraviolet. The Balmer series. It ends on the second level, and its light is visible. Never forget this one. The de Broglie wavelength, Planck's constant, divided by mass times velocity. And Heisenberg's uncertainty, the uncertainty in position times the uncertainty in momentum, is never less than Hg over 4 pi. If all four came to you before the reveal, today's ladder is becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. The Balmer series lies in the visible region. Hold your verdict. Statement 2. Brighter light in the photoelectric effect ejects electrons with more kinetic energy. Think carefully before you answer this one. Statement 3. Heisenberg's uncertainty principle says position and momentum cannot both be known exactly. Picture the ladder as you decide. So, how many are correct? 2 statements, the first and the third. Balmer truly is the visible series, and Heisenberg truly does forbid knowing both at once. But the second one falls. Brightness only changes how many electrons come out, never their energy that comes from frequency alone. That reversal is the trap, and now it will not get you. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. When an electron jumps up to a higher level, the atom gives out light. It sounds active, energetic, so surely it glows. No? David believed this for months. But here is the truth. Jumping up absorbs energy. It is the fall back down that emits light. Up is absorption, down is emission. Keep that direction straight and half the spectrum questions solve themselves. Myth 2. The de Broglie wavelength matters for everyday objects, like a cricket ball flying through the air. The truth, only extremely light particles, like electrons, have a wavelength large enough to matter. A cricket ball's wavelength is so many powers of 10 smaller than the ball itself that it can never be observed. Mass in the denominator crushes it to nothing. Time to test yourself. Rapid fire. And today it leans fully numerical. Here's the rule. I ask, you answer in your head before the reveal and spell each number to yourself. No pen, no paper, just the ladder you built today. Question 1. What is the energy of the ground state of hydrogen? Straight from the formula, with N equal to 1 minus 13.6 electron volts. Question 2. What is the energy of the second level? Minus 13.6 over 4 minus 3.4 electron volts. Question 3. Which level does the Balmer series end on? The second. Balmer always lands on level 2. Question 4. How much energy does it take to ionize hydrogen from its ground state? Lift the electron all the way from minus 13.6 to 0, 13.6 electron volts. And question 5. The thinker. What is the wavelength of the n equals 3 to n equals 2 transition we solved today? about 656 nanometers, the Balmer H alpha line. If you fired back all 5 before the reveal, you have truly understood today's class. Let us gather the whole class in one slow breath. The electron, the proton, and the neutron were discovered one at a time by Thomson, by Goldstein, and by Chadwick. 3 models, Thomson's pudding, Rutherford's tiny nucleus, and Bohr's fixed orbits, each one a repair of the last. Each hydrogen level carries the energy minus 13.6 over n squared in electron volts. The Rydberg formula links those levels to wavelength, and Balmer is the visible series. The photoelectric effect shows that frequency ejects electrons while intensity only counts them, and light carries a dual nature. And de Broglie's matter waves, together with Heisenberg's uncertainty, are exactly what finally broke Bohr's neat fixed orbits. And next class, we go deeper still, into atomic orbitals and electronic configuration, the quantum numbers and the shapes of the s, p, and d orbitals. Do not miss it. And so, my friend, we have stepped inside the atom, G level. It may have felt like a crowd of names, models, and formulas, but hold on to the thread. We learned the inside of the atom entirely from the outside, by scattering particles and by reading light. The tiny nucleus, the ladder of energies, the exact color of a hydrogen atom's glow, none of it was ever seen. All of it was reasoned. And today you turned it into a full numerical besides. Sarah, David, Lisa, and John all sat exactly where you sit now. A little unsure, and they built this picture one rung at a time. Be patient with yourself. Tonight, revise the energy ladder once, slowly, and say the 3 series aloud. One idea at a time, you will crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you among the orbitals.